Hello, in this Vulkan video we are going to do something really exciting now. We are going to do rendering and presentation. We're going to finally show the triangle that we've drawn. So it's been a long process, but we've persevered and we're almost there. So in this we're going to do a few different things, and I think it's best if we just get started. So first of all, at the top we're going to create a const int, call it max underscore frames underscore in underscore flight equals to semicolon. So this basically defines how many frames should actually be processed concurrently, at the same time. This helps prevent memory usage from creeping up, because if they're constantly processing more and more frames, memory usage will creep up. So this will help prevent that. So that is a bug that some people do come across when they start drawing. So it's very important to do. The next thing that we want to do is create a few variables. So if we go to where we create variables, down here, I'm gonna have 4 vectors and 1 number, so an unsigned long. First vector is gonna be std : vector, and it's going to be a vector of vk semaphore. So this is just used to describe how things should be presented. Image available semaphores semicolon std : vector vk semaphore again, and this one's going to be called underscore render finished semaphores, like so. Now we're gonna have a vector of vk fence. There, put the wrong one. Vk fence, and call this underscore in flight fences std : vector vk fence. Images in flight, like so. So next we're gonna have an unsigned long. So this is just gonna track the current frame, be assigned 0 by default. So basically, let me explain what's happening. Each frame should have its own set of semaphores, which is what we're doing now. And frames in flight, will immediately have a synchronization object, which we will be implementing. It basically waits on it before a new frame can use that image. And all of this basically helps ensure no more than the 2 frames of work are queued up at any given time, what we specified above. Obviously, if we change this to a higher number, then it'll dynamically change. That's the way we're going to code this. Next thing is we're going to go down to init Vulkan. So we're going to call another method, create sync objects, which we have not created yet, and it will give us an error at the moment, but we will be creating it. Next, we have not touched main loop for a while, but we will now. We're going to call a method called DrawFrame. Again, we're going to be implementing this later on, DrawFrame. And what we want to do now is after the while loop, at the end of the main loop method, call vk device wait idle, and you specify the device. Okay, so why do we do this? Basically, all of the operations that are going to occur in DrawFrame are asynchronous, which basically means that when we exit the loop in main loop, when we exit, this, drawing and presentation operations could still actually be going on. And you don't want to be cleaning up resources while they're still happening. That is a no-go. That is a very bad idea. Fortunately for us, we can pretty easily fix this issue by waiting for the logical device to finish operation before exiting the main loop and destroying the window. So that's basically what this is going to be doing. Built in, which is pretty cool. Next thing, while we're here, let's clean up let's put for unsigned long I equals 0, I less than max underscore frame underscore in underscore flight I plus plus, like so. And we're going to do vk destroy semaphore underscore device underscore render finish semaphores I no pointer semicolon. We're going to destroy the other semaphore now as well. vk destroy semaphore underscore device underscore image available semaphores I no pointer. And we're going to do vk destroy fence underscore device underscore in-flight fences I no pointer semicolon. And now that we've done the cleanup, we can actually go down and start implementing some of the code that we need to. So first of all, we want to scroll down and go to the render pass method. So create render pass. Should be after this. Here we go. And after we create the subpass, but before we do the render pass info, we want to implement a subpass dependency. And so what is this? So remember that the subpasses in a render pass automatically take care of image layer transitions, and these transitions are controlled by subpass dependencies, which essentially specify memory and execution dependencies between different subpasses. We have only a single subpass right now, but the operations right before and right after the subpass also count as implicit subpasses, so we need to factor that in. And this is a dependency that we're going to be coding in and hooking up to our render path info, which is right here. So I'm going to put vk subpass dependency. I'm going to call it dependency src. I don't want to do that. Subpath equals vk underscore subpath underscore external dependency dot dst, so the destination subpath equals 0, and dependency dot source or src stage mask equals vk underscore pipeline underscore stage underscore color underscore attachment underscore output underscore bit semicolon. Dependency dot source access mask equals 0. Dependency dot dst stage mask equals vk underscore pipeline underscore stage underscore color underscore attachment output bit, again, so the same macro constant. And I'm gonna say dependency dot dst access mask now is gonna be equal to there we go. Just forgot about it a second. Underscore color underscore attachment underscore right underscore bit semicolon. And now if we scroll to the bottom of render path, just need to add a couple of new parameters here for this create info. Render path info dot dependency count. Only one because we're only linking it to one dependency. And for render path info dot p dependencies equals reference to the dependency object. Pretty simple stuff. So now that we've created the dependency, what we are going to do now is actually implement the sync objects method. and the DrawFrames method. So if we scroll down, and we're going to be putting all of this just before the create shader module method. So scroll down, should be coming up soon. So it's going to put it here, which is after the create command buffer, which we did previously in the previous video. So first of all, let's implement the create sync objects method, which is a void, by the way, as you can see. And the first thing we're going to do is match the semaphore sizes with the maximum number of frames in flight. So I'm going to put underscore image variable semaphores dot resize, and this is just going to be equal to max frames in flight. Copy and paste this. Just replace this with the render finished semaphores, and we're going to do something similar again. And we're going to put underscore in flight fences, so we match the fences as well. Next, we're going to match the images in flight size to the swap chain images size. Underscore images in flight dot resize, and we'll say underscore swap chain images dot size, and I'm gonna put a vk underscore null handle, so you'll just assign that value to it. Okay, so what we're gonna do now is create the semaphore create info object. So vk semaphore create info, vk semaphore create info, semaphore info, semaphore info dot s type equals vk underscore structure underscore type underscore semaphore create info, and we put vk fence create info. So we're going to create the info object for the fence now. So we're going to say, call it fence info, and we'll say fence info dot s type equals vk underscore structure underscore type underscore fence underscore create info, fence info dot flags equals vk underscore fence underscore create underscore signaled underscore bit. Now what we're going to do, the final thing, is create all the semaphore and fences, and we're just going to loop through and create all these, and it's going to be in line with the maximum frames in flight constant. So we're going to for unsigned long I equals 0, I less than max underscore frames in flight I plus plus, and we're going to say if vk create semaphore, so I'm going to say underscore device, and pass in the semaphore info, pass in null pointer for callback, and pass in a reference to the vector of image available semaphores. And I'm going to say if this is not equal to vk underscore success, there we go, or so basically if one of these fail, then we're going to throw a runtime error. So we're going to basically do this again. If I just copy and paste it, it'll just save me a bit of time. So create semaphore device and semaphore info, no pointer, but for this one we'll say underscore render finished semaphores not equal to vk underscore success, and finally here we're going to say vk create fence underscore device, reference to the fence info object, put a null pointer for the the callbacks, for a reference to the in-flight fences vector, and while that is not equal to vk underscore success, then we're just going to say throw. So if one of them fails to, create, we're going to say std : runtime error, and we're going to say failed to create synchronization objects for a frame. Okay, so next what we are going to do is create the DrawFrame method, and then we're done. So this is the last thing we're going to do, and then the triangle will display. First of all, we need to wait for the frame to be finished. So we put vk wait for fences, and we specify the Vulkan device, and the count is just 1. Then we specify a reference to the in-flight fences, and it's going to put current frame. That's the one that we're going to be, checking, and waiting for. I'm going to say vk underscore true for wait for all, and then for the timeout, we're just going to say u int 64 underscore max. Okay, so now what we're going to do is get the next image to be drawn. So I'm going to say unsigned int, call it image index. I'm going to say vk acquire next image khr, and you specify the Vulkan device, the swap chain, and the timeout again is the same. So u int 64 max. You specify the available semaphores, so underscore image available semaphores, and we're gonna get current frame, and close double square bracket, vk underscore no handle, and a reference to image index. Okay, so next we're gonna make sure the image is not null. So we say if underscore images in flight, and check the image index, check the one at image index, I should say. If it's not equal to vk underscore no handle, we can wait. I come German. Wait for the fences. So vk wait for fences underscore device, and for the count it's going to be 1. For the fences it's going to be a reference to underscore images in flight at image index, vk underscore true to wait, and we'll say u int 64 max again for the timeout. Okay, so now that we've done that, the next thing that we're going to do is match the in-flight images to the current frame. To do that, we put underscore images in flight image index equals to underscore in flight fences current frame semicolon. Okay, so next we're going to queue submission and the synchronization, and configure it through parameters in the vk submit info structure object. So I'm going to say vk submit info, call it submit info, say submit info.type equals vk underscore structure underscore type underscore submit underscore info. Okay, so now that we've got that, what we're going to be doing now is creating the vk semaphore, and to do that it's not too difficult. We are approaching the end. A lot of code here, but we're getting there. Okay, so we're going to say vk semaphore, call it wait semaphores, and equal to underscore image available semaphores and the current frame. Okay, so here, these parameters that we're going to set will specify which semaphores to wait on before the actual execution begins and in which stages of the pipeline to wait. So we're going to put vk pipeline stage flags wait stages equals vk underscore pipeline underscore stage underscore color underscore attachment underscore output underscore bit. And we're going to set the wait semaphore count. So I'm going to say submit info, which is what we created before, dot wait semaphore count equals 1. Submit info dot p wait semaphores equals wait semaphore that we just created. Submit info dot p wait stage math equals wait stages. Okay, so now what we're going to say is we're going to implement the command buffer count and the command buffers, and each entry in the wait stage array corresponds to the semaphore with the same index in the p-wait semaphores. So that's basically what we've just done right here. And now what we're going to do is specify the command buffers. So these two parameters that we're going to set will specify which command buffers to actually submit for execution. So I'm going to say submit info dot command buffer count equals 1. Submit info dot p command buffers equals reference to underscore command buffers image index, like so. Okay, so now we're going to set up the signal semaphore. So we'll say vk semaphore signal semaphore equals underscore render finished semaphores current frame and submit info dot signal semaphore count equals 1. Submit info dot p signal semaphores equals signal semaphore, and we're gonna reset the fences now. So vk, let me scroll up a bit so it's easier for you to see. Vk reset there we go, and we just specify the device, specify the fence count, which is 1, a reference to the fences, so underscore in flight fences, and the current frame that we are resetting. Okay, so what we need to do now is try and submit the queue. So we'll say if vkq submit, there we go. And we're going to specify the graphics queue first, then count, which is just 1 submit info, then a reference to submit info, underscore in flight fences, current frame, and we're going to see if that is, we need to put a square bracket here, if it's not equal to vk underscore success. If it isn't, we'll throw a runtime error. Put failed to submit draw command buffer. There we go. Okay, so almost done. We got like 10 lines of code roughly. So the last step of drawing a frame is submitting the result to the swap chain and to have it eventually shown up on the screen. And we'll create a vk present info khr for this, call it present info curly braces like so. And now we're going to specify which semaphores to wait on before presentation can happen, just like we did in submit info. So I'm going to say presentinfo.type equals vk underscore structure underscore type. Spelled structure wrong, put a y in there. My bad. Structure underscore type underscore present underscore info underscore khr. I'm gonna say present info dot wait semaphore count equals 1. Present info dot p wait semaphores equals signal semaphore. Yeah. Probably best if we name this to signal semaphores, just because the source code does actually have signal semaphores there. So just to keep things in line as much as possible. And I don't want to honestly confuse myself as well. That would be the last thing that we want. Okay, so what was we doing? We were doing the present info, and we had just set the signal semaphores. And okay, so now that we've done that, what we're going to do now is specify the swap chains to present images to and the index of the image for each swap chain. And basically this will almost always be a single one, so the count will be 1. So I'm going to put vk swap chain khr, call it swap chains equals, to make sure you put curly braces, underscore swap chain that we implemented many videos ago, present info.swap chain count equals 1, and we just link up the swap chain. So present info.p swap chain equals underscore the swap chains, and we're gonna put present info.p image indices equals a reference to the image index that we created right at the top here. It was created here somewhere. There we go. And almost done. Now we submit the request to present an image to the swap chain. So I'm gonna say vk q present khr, almost done, underscore present q, and then you pass in a reference to present info. And now finally we move to the next frame every single time that this method comes to the end, and we will use the modulus operator, which will ensure that the frame index loops around after every max frames in flight number that we created right at the top. So we're going to put current frame equals current frame plus 1. Obviously you could just do that, but to make sure it loops around, we'll just modulus it with this, and I think we're all good to go. I think hopefully we shouldn't have any errors. Again, the same error there. Sometimes when you build it, that disappears. If it doesn't, we'll figure out what it is. We got some error somewhere. That was a very early error. Okay, I mean in the video, that is. Okay. So all the validation layers. There we go. We have the triangle. You might be thinking, if I just launch it up again. And again, we got no problems. We had, the anisotropy enable problem before, but that's fine. If I run it again, so yeah, you can see nothing draws because of all the validation, layer checks. So if you don't want that and you want it to load as instantly as possible, remember when we put this, we can disable validation layers just by putting hash define and debug. If I run that now, this one gets highlighted. Validation layer is now false. The triangle is drawn virtually immediately. So I would say just leave that there. If you wanted validation layers enabled, you comment that, press run, and this time it's actually going to go through all the validation layers And there we go. So finally we have a triangle. And yeah, it's been a long journey. If you have any questions, feel free to message us on our Discord group. There's a link in the description. In our Discord group, there's a specific Vulkan channel, so feel free to hit that up. There's over 5,000 members now, so the community is growing every single day. And also the link in the description to the GitHub page, which will provide you with all the source code from this video, every other video, and working projects as well. So you can just download it, run it, manipulate a few lines of code instead of having to go through the whole setup process if you want to. And that's it. If you have any questions, you know what to do. And as usual, I look forward to seeing you in the next video.